All right, so this next unit, or next, I guess, section, is going to be about matter. So the goal, I guess, of this unit is to make sure that you can classify matter based off of its properties. All right, so chemistry deals with identification of substances, and all substances are made out of matter. So the idea is that we can predict, well, first of all, we need to learn about matter. We can figure out how matter can change, and then we can use that to predict how maybe unknown substances can behave. All right, so chemistry is basically the study of everything around us, because everything that we know is composed of matter. Okay, so again, if we want to understand the substances around us, we need to be able to understand the atoms and the molecules that compose those substances. And that, again, is that central goal of chemistry, to study the world around us, to study the behavior of atoms, study the behavior of molecules, to figure out and then learn more about the behavior of matter. So like you've learned probably in middle school, and then again in physical science, and now again in chemistry, that matter is anything that takes up space and has mass. Right, so a lot of times I'll ask my students, do you think that air would be considered matter? Right, and yes, it is. Right, it does take up space. So if you've ever, put a cup into water, an empty cup into water upside down, it takes up space. It doesn't automatically fill up with, that cup doesn't automatically fill up with water because there's air taking up space. So if you kind of tip it to the side, that air will escape and then water will go in. All right, so it does take up space, and air also has a mass. It might be really, really small, but it does have one. All right, so when we want to describe matter, we can classify it in a number of ways. So we have extensive or intensive properties. We can talk about it in terms of whether it's a physical or a chemical property, or we can talk about the state of matter. So we're just going to go in order here. The first way that we're going to describe matter is by saying whether it has extensive or intensive properties, right? And matter actually has both kinds. It's just how we classify it here. All right, so here's the first definition. An extensive property is a property that depends on the amount of matter in a sample. All right, so some examples are mass. All right, if you have more matter in a sample, mass is going to change. That mass is going to go up. If you have less matter, mass will go down. All right, so another example is volume. So if you have more matter, yes, that matter is going to take up more space. The volume will be larger. If you have less matter, your volume should not be quite as large. Length is another example of an extensive property. It's going to depend on the amount of matter. Okay, so if, let's say I'm talking about like a string. The longer the string, the more matter in that string. Okay, so an extensive property is one that depends on the amount of matter in a sample. All right, and one way to remember that it depends on the amount is, remember, E stands for elephant, lots of mass and volume. So those are actually two examples of extensive properties. You could remember E for extensive and E for elephant. Okay, it depends on how much of the matter there is. The next way that we can describe matter is by its intensive properties. So an intensive property is one that depends on the type of matter in a sample, not the amount. All right, so an intensive property depends on type, not the amount. So an example is the temperature of a substance. Let's say that temperature of a substance at its boiling point. Okay, it doesn't matter, let's say, how much water you have, it's always going to boil at the same temperature. It might take longer to get to that temperature, but it's always going to boil at the same temperature. Same thing with freezing. So color, right? Doesn't matter how much of a substance you have, that color of that substance is not going to change. Okay, you have a swimming pool full of water, adding a few more drops or, adding another swimming pool worth of water, it's not going to change the color. The fact that it's water is what gives it its color, intensive property. Hardness, so if you're looking at maybe hardness of different minerals, and again, minerals are made out of chemical compounds, so that can be an example of an intensive property. Okay, it doesn't matter how big of a rock you have, it's going to have the same level of hardness. Melting point, boiling point, that kind of goes along with temperature there. And then density is actually an intensive property. Remember, density is one of those properties that is used to define a certain chemical or a certain mineral or a certain, a certain compound. Density can identify those things. Okay, so it doesn't matter about how much of a substance you have, its density will always be the same. And if you think about the formula for density, density is mass over volume. Both of these guys are extensive, right? We said mass was extensive. It depends on how much of a substance you have. So if I have more of a substance, this mass number is going to go up. Right? We said volume is also extensive. Again, if I have more of a substance, that volume is going to go up. But these two correspond with each other. If I have more of a substance, both of these are going to increase, but the ratio of the two stays the same. Okay, so that density does not change, which is what makes it intensive. It won't depend on the amount. It just depends on the type of matter in the sample. All right. The other way that we can describe define matter is by its physical and chemical properties. Okay, so you've probably learned about this in physical science, but we'll do a quick recap here. So whenever we're talking about physical properties, these are qualities or conditions of a substance that we can observe or measure without changing the composition of whatever we're testing. Okay, so that can be observed or measured without, oh, that's an ugly I, without changing the composition of the substance. Okay, so what I mean by that is, again, it's not going to change what the substance is. So an example of a physical property is maybe boiling point, which is a temperature. I can test the boiling point and figure out what the boiling point is of water, but I'm not changing the fact that it's water. It's going to stay water. Another physical property can be measuring the density. Right? I can measure the mass and the volume of a substance, but just because I did that doesn't mean that it magically turns into something else. It's going to remain the same substance. Another physical property could be color. Again, just by saying, oh my gosh, this can is purple, doesn't change the fact that it's a can and it's made out of aluminum. An example, the other way that we can describe properties is by defining a substance's chemical properties. So these can be observed by reacting the substance. All right, so just the fact that you see by reacting gives you an idea that it's different than a physical property because it does change the composition of the substance. So it can only be observed by reacting the substance, therefore changing its composition. All right, so let's think about ways that we can change the identity of a substance. We can change the identity of substance by reacting it with something. So there is a term called reactivity. All right, if a chemical or an element is highly reactive, that means it's going to, be able to react with a lot of different substances. But remember, after it does that, it's not the same thing. That's the definition of the word reaction. Another example of a chemical property could be the flammability of something. After I figure out that a substance is flammable, well, I definitely don't have the same material anymore, right? So flammability. All right, so those two are examples of chemical properties. All right, so how do you know if a chemical change has occurred? So some clues to a chemical change are that there is a change in energy. So maybe heat or light are given off or absorbed. Remember, heat doesn't necessarily have to be given off. It could be absorbed. So either one of those. A change in color. The main idea here is that the change in color is unexpected. All right, so if I have like food coloring and I put it into a glass of water and it changes color, yeah, that's kind of what I was expecting to happen. It's more like you mix two chemicals together and that are clear and colorless, and then they turn into this like bright yellow. Okay, that's an unexpected change in color. If there's gas production, so this would be like, you would never write this on a lab, but a gas production would be if you see bubbles being formed. All right, please don't write bubbles on a lab. You could write gas produced. And then another sign for a chemical change is a precipitate. So precipitate is a fancy way of saying that a solid is formed. All right, so a solid is formed. Usually the short way to write precipitate, since it's kind of a long, complicated word, is this, PPT. So you could say, there's like white chunky things floating around. You would never say that, but if you did see that, you could say white precipitate formed. All right, so that would be kind of like a snow globe looking thing. All right, so identify the change. You guys can do this on your own. I guess just a heads up, all of these pictures have the same like beginning slide, or I guess all of these videos have the same beginning picture. Just so you know, they do all examine different changes once you actually click play. All right, so I'm gonna go through these because you can do that on your own in your own presentation. All right, so whenever we're talking about chemical reactions or even physical changes, they both follow this law of conservation of mass. All right, so the idea of this, again, you probably know what the word conservation means, is that you're saving something, right? So that's what happens with mass. Matter, which remember has mass, is neither created or destroyed, but it can change forms. All right, so this law of conservation of mass means that if you were able to collect all of the products of a chemical reaction, there's going to be no loss of mass. So if I mass everything before the reaction, and then I let the reaction happen, and I mass everything after, those gram amounts should be exactly the same. Right, and the same is true for physical changes. Right, it only makes sense if you have 100 grams of ice and you let it melt, that you have 100 grams of water. Right? It's not going to magically appear or disappear. Matter is neither created or destroyed. So it can change form. So this was a solid when I said ice, and it can change into a liquid, but it's not going to turn into something else. It's not going, the mass isn't going to, just go down to like 95 grams or something because it melted. It stays the same. So that's what the law of conservation of mass is. You should watch this video here. It does a really good job of explaining why the law of conservation of mass is actually true and how it holds true. All right, so this should look very familiar to you guys from physical science and then possibly even like middle school science. All right, so here we have our 3 states of matter. This is the last way that we can describe matter, at least the last way that we are going to be describing matter in this class. So a solid, you can see here in letter C. All right, so we can tell ourselves, hey, solid is found in picture C. If we take a look at those particles, right, they are neatly organized, tightly packed, tightly packed. All right, there is a constant volume. And then it holds a consistent shape. So I'll just say constant. Right, for the liquid and the gas, I'll just talk about them, but I won't write them to save some time, and you guys can do that. All right, so again, a solid, take a look at those particles. They are neatly organized, tightly packed. Solids have a constant volume, so just because, let's say I change the environment of a pencil, either on the desk or on the floor, the volume doesn't change, and neither does the shape. Okay, so constant volume and a constant shape. All right, let's take a look at our next state of matter, which is a liquid. So a liquid is beaker B. All right, and you can see that the particles are still tightly packed, but not quite as close as the solid. All right, so just pay attention to that. They're kind of like the intermediate, not as far apart as the gas, which is A, but not as close together as a solid. They're not neatly organized, okay? So those particles are kind of like on top of each other, moving past each other, so not really neatly organized. Liquids do have a constant volume. So I could have 10 milliliters that I've measured out in a graduated cylinder and poured into a beaker, and it looks different, but it's still 10 milliliters. So the volume is constant, but it does not have a constant shape. Okay, water's shape fits whatever container we put it in. All right, the next state of matter and last state of matter that we are going to be talking about is a gas. All right, so that is beaker A, and one way that you can tell that it's a gas is that it is total chaos. If you take a look at the particles, they have these kind of like black shadows after them. It just means that they're moving those particles are moving extremely quickly. So they're spaced out, moving super fast. And then in terms of volume and shape, not constant volume. Okay, notice how this container had its lid taken off, so now the air particle or gas particles are taking up more space, so not a constant volume, and they also don't have a constant shape. Similar to a liquid, they're going to take the shape of whatever container they're in. So an example of that could be a balloon. All right, so you have a helium balloon, those particles are filling it up. At the time that those particles are in the balloon, that's the shape and that's the volume. But if I pop that balloon, those particles are out of there. All right, so now they have a different shape, they have a different volume because they're spreading out. All right, so now we need to do a quick recap about heating and cooling. So these are phase changes. We can talk about heating a solid, heating a liquid, and then cooling a gas down, cooling a liquid down. And this is all going to result in different phase changes. Remember, just because we're changing the material from a solid to a liquid to a gas, and then vice versa, doesn't mean that we're doing a chemical change. It's still the same substance, but in a different phase. So I do want to remind you guys that these are phase changes, which are physical changes. I'm just changing, I guess, the state of matter, but I'm not changing what the material is. So these are all physical. I'm not reacting the substances. All I'm doing is adding and removing heat. All right, so I'll switch to red and we'll go over the top part of this picture. You'll notice that the top part, it says that we are adding energy. Right? Anytime that we are adding energy, this is called an endothermic change. Endothermic. Right? So you might recognize thermic, like thermometer, has to deal with temperature, has to deal with heat. And then endo means into, which means that we are adding energy into whatever material we're looking at. All right, so the first arrow here, we have a solid changing into a liquid. All right, so this first arrow right here, notice how the solid particles, again, there might be a little bit of vibration in the particles, which is why they're showing this like one little line. In a liquid, you can see two lines, so there's more movement. Notice how they're not as organized and a little more spaced apart than the solid. All right, and then notice the gas. Okay, so first of all, we just have less particles in the picture, not because the liquid and the solid didn't create the same amount. It's just because they've already moved out of the way. Notice those three lines. These are moving super fast, spaced out, and that's about it. All right, so now the two phase changes on the top. All right, so we've got a solid changing to a liquid. If you're ever stuck on phase changes, what I always tell my students is think about ice. You're really familiar with water and ice. All right, so a solid, water, would be ice. Let's say we're turning it into a liquid. All right, that is called melting. All right, melting requires heat, okay, which is why it's an endothermic process. All right, now the next arrow, going from a liquid to a gas. All right, so that change, so again, liquid, think about liquid water, and then we're turning it into water vapor. All right, so this is vaporization. All right, and I did say, think about water, but these words hold true for any substance. Melting, vaporization, those mean the same changes. All right, so again, melting is from a solid to a liquid, and then vaporization is from a liquid to a gas. Okay, so now we're going to go down to the bottom, which has the opposite phase changes. And these are blue because these require the removal of heat energy. All right, so when you remove heat energy, those are called exothermic changes. Oops, I can't fit it, so I'm going to write it here. All right, exothermic. So just think about it this way. Again, thermic deals with temperature. Think about it like a thermometer. And exo sounds like exit. So heat has to leave to make this happen. All right, so our first arrow, so I'm going to go to this arrow here on the right, from a gas to a liquid. So think about water. Water vapor in the air. When it cools down, it turns into a liquid, into like water droplets. So this is called condensation. All right, and then our next arrow going from a liquid to a solid. All right, so again, think about liquid water, and we're making it into ice. This is called freezing. Again, I'm using water as my example, but these words for phase changes can be used for any substance. All right, so this is opposite. Condensation is from gas to liquid, and then freezing is from liquid to gas. All right, so taking a look at an example here of a heating curve. So just a quick recap about what heating curves are. They show the heating or cooling. All right, so then this would be called cooling curve, but this one says heating curve. So in this case, if you notice that what's happening over time is that the temperature is increasing. Overall, there's like a positive slope to this line, so we know that this is a heating curve. If, and I know this isn't, just want to make sure it's not on the next slide, but if this was a cooling curve, you would see temperature going down over time. Okay, but again, that's not what's happening here. So think about what happens to a substance at its lowest temperature. Which phase of matter is it going to be at its lowest temperature? Right, so down here at the lowest temperature, this is where we would have a solid. Right, and if you notice, this line from A to B is slanted. That means that temperature is increasing while the substance is a solid. That makes sense, right? If you have an ice cube, you can heat it up, right? So the solid can be heated up. So the next phase, and I'm going to skip over BC, is right here. I'm going to go CD. All right, this is where we would have a liquid. So again, the substance is not at the lowest possible temperature, but here it's kind of like at the intermediate temperature. You guessed it, at the highest temperature, a substance is going to be in its gas form. All right, so the reason I omitted the flat lines is because that's where those phase changes are occurring. All right, so BC, we have the substance changing from a solid to a liquid. And I only know this because I can take a look, like down here it's a solid, up here it's a liquid. So here's where it's changing. Okay, so we're not going to label this solid to liquid. We're going to call it the phase change. So again, when we go up here, a solid changing to a liquid is called melting. So this is where the substance is melting. I'm going to zoom in. All right, and if you look at that temperature, it's not changing during melting. And that sounds kind of weird, but that is absolutely true. Okay, and you'll see this when we do our lab. As a substance is melting, its temperature does not change. It actually stays at the same temperature until every single particle is changed from a solid, and then the temperature can increase because it's already in its liquid form. But while a substance is melting, its temperature does not change. All right, if we take a look at section DE, Okay, so here we can see that this section is between the liquid and the gas phases. All right, so we can kind of take a sneak peek here. All right, the difference between our liquid to a gas. Oh, here we're going to have vaporization. All right, so you probably noticed, again, temperature does not change. All right, so again, it sounds weird, but you need to remember that. All right, so put a big star on here. Temperature does not change. Not, in caps, underlined, change during phase changes. All right, so temperature does not change during phase changes. The only two phase changes that I showed you here were melting and vaporization. But don't forget, there's also condensation and freezing. The same holds true for those two. Temperature does not change while a substance is condensing or while a substance is freezing. Those are always going to be the flat parts of your line. Okay, so phase changes are always the flat parts of your line because temperature does not change during a phase change. All right, don't forget that. All right, so we do have more phase changes than we've mentioned. So we've already talked about condensation and vaporization. We've talked about melting and freezing. These two you might have to do like a little refresher on: sublimation and deposition. All right, so if you take a look, sublimation, pick a different color here. All right, sublimation is the change from a solid to a gas. All right, so you might want to write this down: solid to a gas, sublimation. All right, so an example of this would be dry ice. All right, so if you've ever used dry ice, maybe like in your cooler when you've gone camping, or if you've ever seen dry ice, if you receive packages, whatever, that need to stay frozen. This is why dry ice is used, because there's no liquid phase. It's really nice and clean. And when it melts, which again, it doesn't, it sublimates, it just turns directly into a gas. All right, so solid directly into a gas, skipping over that liquid phase, is called sublimation. The opposite of this, and I'll just pick a random color here, purple. All right, a gas to a solid is called deposition. So gas to solid, deposition. All right, same deal. There is no liquid phase. So this is something that goes directly from the gas form into a solid. So the example that I'd like to use is frost on a window. All right, so if it's really humid but cold outside, and you have water vapor in the air, and remember that's an example of gas, and it hits the window, cold window, it's going to turn directly into that frost. All right, and I'm not talking about the frost that's like drippy and melting off. Like initially when it's first formed and the window from the inside's not like heating it, when you just have like a cold window and the water vapor on the outside. So this could be like frost on window.